Hello everyone, NadLabs here. Today we're going to be making this program in the Godot game engine, which actually can learn from itself and is able to get better and better, and I'm actually hinting on the idea of a genetic algorithm or an artificial intelligence. Genetic algorithms are a type of artificial intelligence. I'm going to give a couple disclaimers. I'm not really good when it comes to AI, and I'm going to be completely honest, I had to learn a lot from YouTube and reading. I had to go a lot towards CodeBullet, Coding Train, MIT OpenCourseWare. I had to go to all these different videos and websites to learn, and this is just my attempt on understanding AI, and I just thought I would make a video while I'm at it, so I decided to do it in the Godot game engine. And another disclaimer, you don't really need a good PC. As you can see, I'm rocking a GT 1030. Like it's not even a GTX, so you don't need a good graphics card, nor do you need a really good CPU. Like I have a 10-year-old CPU here with DDR2 memory, so I'm trying to say you do not need a really good CPU or computer to actually run this program on your computer. And yeah, I'm just trying to help people get into the basics of machine learning right now and artificial intelligence. So with that being said, let's get right into it. But to get right into it, we have to first understand what we're actually going to be doing. So we're basically going to define a game scene. So this is game scene. And then in our game scene, we're going to have these little creatures which can freely move about, okay? They can move around in any direction, and they're going to remember the directions they moved in through something called a genome, okay? This genome that we are making is going to be an array of directions. So it's just going to be a vector 2, and we're going to have an arbitrary amount. You can put whatever you want. I chose 75 because I found that was a good number that my computer could handle. So we're going to have like 75 directions. So this is like the second one. This is the first one. 75 directions. And these creatures are going to just randomly move about in any direction they please. As you saw in the beginning of the video, we're just moving around randomly, and then they slowly got better. We're going to implement that as well. So we're going to have to define a goal. So our goal will just be a red square. So now we have our goal, and it's just going to be a red square in area 2D. We're going to have to decide how we are going to move our creature. I chose to go with an area 2D, and we're going to just be saying the global, not area 2P, area 2D, and we're just going to be saying global position, and then we're just going to do plus equals the direction, okay? And that's basically all we're going to be saying. And then on top of that, we're going to be saying every like 0.05 seconds, we're going to switch our direction, this direction variable, to be the next part in the genome, the next part, and hopefully when we get to the end, we're just going to either consider the creature dead, or if it touched the goal, or if it touched the wall, we're also going to consider it dead, and we're just going to stop the genome prematurely. That's all we're really going to be saying and doing. For the first gen, we have to just say, you know what, pick a random genome. So you're going to take this array, and you're just going to say for I in the array, or for I in 75 technically, if you're using GDScript, we're just going to say I dot, we're going to say I equals some random number, some like random number, like that doesn't even matter. Or we're going to say at least the genome dot I, the bracket notation, to get that specific index of the genome. We're just going to send it to some random direction. Anything that is not second gen, not first gen, so second gen, third generation, fourth generation, fifth generation, not first generation. If you're not first generation, you're going to take the best genome that we could ever come up with, and I'm going to explain how we get the best genome ever. You're going to take that best genome, and you're going to just mutate it. So if the original best genome had like 75 points of 75 directions, let's just consider those directions. I don't know why it's not making dots. If it had 75 directions, you're just going to take like maybe 0.05, so 5%, or 10%, maybe 2%, and you're just going to slightly move them over. Like instead of pointing in this direction, you can choose an entirely new direction, or you can, if this was the original direction, you can like slightly move it that way. Whatever you want, you can just do that, and this will be considered mutating our genome. To mutate that creature's genome, this is all we're going to be saying, and this will lead to maybe if the first generation moves around this way, right? Then maybe this second generation would move something like this. They're still moving in the same general direction because maybe this part is exactly the same as this part, but maybe this part over here was replaced with something like this, and therefore the entire movement was changed, and thus it's actually closer to the goal as compared to this one over here. And because this guy's closer, we're going to say, okay, this is the best genome ever, and now you're going to repeat, and we're just going to follow this process all over again, this purple line process. And we're just going to say next generation, mutate the genome and continue moving. And then the next generation will do something like that, and it'll get even closer because for some reason the genome just happened to be closer. As you can see, the way we're telling who's closest is literally by saying global position, subtract goal.global position, and then that's basically it. And we're actually going to be squaring the distance between these, so that actually has two benefits. We're going to have a faster computation because we don't have to square root the number, right? We're using Pythagorean's theorem to find the distance. And then on top of that, it actually helps us narrow out the people who are really far away, because if you have a distance like this, as compared to a distance like this guy seems horribly worse because the distance is squared. Whereas this creature over here, she might be like, oh, I'm really close, so I'm actually really good. And another creature might be over here, and they might be like, I'm even closer. I have the distance squared. We're actually going to be doing something a little counterintuitive. We're going to say that if a creature is really far away, they have a really high fitness score, okay? A really high fitness score is bad in this scenario just because it's easier and we don't have to do any like extra work. We're just going to say a high fitness is bad. A small fitness, so like we'll have to just subtract a really small value. This is good. Small fitness of like maybe 250 or 500 pixels squared. Remember, this is a squared value. So if we actually square root something like that, so let's say we have, I don't know, like the difference between these squared is 144. We're actually like 12 pixels away. And 12 pixels is really close, but it might seem far away with this 144. So you'll actually see that the best fitness we have at the beginning of the game or the program is actually a really large number, because we want to make sure that any person, any creature who gets close to the goal will get in. I'm starting to realize this looks really messy, so hopefully the code that we can dive into is even better. If not, if the code that I explain in the next few minutes, 5-10 minutes, isn't helpful, or if it's really confusing, please comment down below and ask. I'll try my best to explain it. And I really don't want to ask, but if you could please consider subscribing, because these videos actually take quite a lot of work. So with that being said, let's jump into the code. Okay, so here's our scene. We have our main scene, right? We have our tile map, and I'm just going to go over the tile map. So we have just a black square, and I try my best not to make this a game with many assets, but you kind of need like a black square or a white square. That really comes in handy. So we're just going to define a region. So you can see I just defined a region of the black square. Then I set the collision shape to that black square, like that's really obvious. If you're having trouble with the snapping, you can just go over here. So you actually have to first draw a collision shape. So you actually have to first draw it, and then an option will appear, which is snap options. And then you can actually manually change the step size to fit your square perfectly. That's something I don't like about the tile maps in Godot. You have to actually draw it out before you can edit it for some reason. Oops, let me just fix that. Yeah. So tile maps all set up. We have a timer. I'll explain this timer when we have to get to it. And we have our goal. We can see that we have a simple goal. It has a group of goal. That's really important. And we don't have any script attached to it. That's all we need for the goal. And that's really all we're going to be doing. And for our creature, we have area 2D with a sprite, because I actually want to see it. We have a collision shape, so we can define where it hits and when it hits. And we have our timer. I'm not 100% sure if I remember saying this, but I said that we were going to move by our direction every 0.05 seconds. Every 0.05 seconds, we're going to go to a new spot in the genome. That new spot in the genome directly correlates to another position in the genome. And I hope that makes sense. So we're just going to be moving across the genome. So it'll make a lot more sense when we code it out. So let's get right into that. So we're going to start off with a couple variables. And I know dead and alive are basically the same thing, but trust me, it helps a lot more in understanding if you have these variables separated, even though that they're the exact same thing. Just separate them out, please. Then you have your original. This is to check if we have a first generation or a not first generation. We have our speed. This is just how fast the creature will be going. We have our genome, which is just an array. You can see that this was also an array. I used the brackets over here. We have our spot in the genome. That directly correlates to which gene we're looking at, if you will. We have our fitness. That was the fitness I was talking about over here. How far away you are from the goal.global position. Then we have our goal, which is actually literally just the red square that I drew over there. Then we have our genome size. That's how many genes we're going to have. So I wrote 75 over here in this really disgusting way. So we're going to have 75 genes, and these 75 genes dictate how we're going to move. That's all that is. And we have our mutation amount, which directly correlates to let's go with green. Which directly correlates to if we have not a first gen, how many of these are we going to mutate? So if it was like a mutation rate of 1, every single one of these points would be mutated, so all of our directions would be mutated. And if we had a mutation rate of 0.05, which is what we have, so 5%, maybe we'll have like, maybe like 5 or 2 or 3 of these directions or genes mutated out of our entire 75 batch. So these are all the variables we're going to need. So then we're going to go into our ready function and just say for I in genome size, genome.append vector2.0. The reason we're doing this is so we can make sure our genome has 75 points. Because for I in genome size, so let me just print I. Hopefully Godot does not crash, or at least I'll get to be able to, yeah, so you can say I can print out 75 things because we start at 0. Let's consider this 1. So this becomes 2, this becomes 3, and if we follow that logic, this value is technically 75. So we have 75 genes in our genome, but they're all set to 0. So then we're going to call our randomize function, and then we're going to say, so then we are going to set our goal variable to the goal node. And the way we're doing this is because we're spawning everything in the creature folder, we're going to say, let me just put a creature in for 1 second. We're going to say creature, go up 1, so get parent, then get parent, then get the goal node. So that's simple. That's as simple as it is. So then we're going to talk about getting the genome and actually saving it and going through different iterations of it. So you can see this code's kind of complex, but it's also kind of not. So let me explain. We're going to say if global.bestDNA equals null. What's global.bestDNA? Well, remember I was talking about how we have this direction, this array of directions over here. Well, I'm actually trying to say that this is the best genome. Remember we were talking about the just best genome? This best genome is actually going to be saved in global.bestDNA. How did I get global dot? So that's actually a global variable. And I know I shouldn't be using them, but it makes it really easy for this project. So to make a global variable, you have to go to new script, type in global.gd or whatever you want. So I already have one. You can see it's literally just this really simple script. And using that global.gd, you go to your project settings, you go to autoload, and then you just find that file and you click add. It adds it as a singleton or auto load script, and these variables are now available in any script I go to. So we have var best DNA. It's currently set to nothing. We have our best fit. Remember the best fit over here. This was our best variable. How far was someone from the goal.global position? And then we have our generation number. Generation number, I hope makes sense. It's just how many generations we've gone through. So we're going to say if the global.bestDNA equals to null, we have an original person. We're going to set our genome to some random vector. So this is actually the first generation. We're just going to set it to a random dir. Hopefully you guys can see that. It just says random dir. Just says random dir. That's all. But if the global.bestDNA is not equal to null, right? This is our else statement. If it's not equal to null, we obviously have a second generation. And we're just going to say the exact same thing, right? We're saying for I in genome size, you can see it highlights the same stuff. We're saying the same thing. Get a random variable only if a random float has a smaller value than our mutation amount. Since 0.05 is really small, the chances of a random float having this value, having a value less than 0.05 is really small. So we're only mutating small parts of our genome. Else we're just going to set the same thing. We're just going to set global.bestDNA, this specific index, to this specific index. So I'm hoping I'm making sense. We're basically saying keep the same genome, keep the same gene, not genome, keep the same gene. And here we're saying mutate that gene. And the way we're mutating it is we're just saying, just replace it with something completely brand new. I hope the ready function makes sense. Let's move on to a different function. So now we're moving on to our physics process function, and you can see I don't have the function die available, so I'm just going to quickly make that. So here's our die function. So we're going to say if you are alive, and we're doing another check, and I know this is kind of redundant, but it really helps. And we're going to say if we are not dead, and our spot in genome is less than the genome size, add to our global position. So this doesn't make sense because we haven't brought in a different function. I actually need to bring in a timer timeout function, which makes the physics process function make sense. So I'm actually going to connect the signal. So let me just go over there, and I'm just going to click connect, and you can see it connects to this signal. I already had it connected, but we're basically saying for this timer, which is has a wait time of 0.05 and auto starts, we're going to say every time it times out, if you are alive, and we obviously when the creature starts out, it's going to be alive, and I'll show you where that becomes alive. When we're instantiating or placing our creature in the main scene, we actually set the alive variable to true, but right now it's false. I'll explain the reason later on. So if we are alive, which we will be when we are making the creature, and we're going to add 1 to our spot in the genome. Our spot in the genome directly correlates to which direction are we looking at. Because remember, we have to like navigate our directions. So then we're going to say spot in the genome plus equals 1, and then it directly correlates to this variable over here, which says if the spot in genome is less than genome size, we're still alive. We're going to say global position plus equals genome spot in the genome. I'm hoping this makes sense. It basically means, I usually find that the best sentence I make are when I type them out. So that's basically what it means. We add 1 to the index we are looking at after we are done with that gene. So then after we're done that with that gene, we move on to the next gene, next gene, next gene. And it'll make a lot more sense if I just say something like, let's say these are directions, right? We're moving in these directions somehow. Let's say we're just moving in this direction, right? We're basically saying, go to the next one, go to the next one, go to the next one. Keep adding these to the global position. Let's say we're only moving on the X direction. Keep adding these to the global position. And that's essentially what we're saying. I'm really hoping this makes sense. If I could get some confirmation that this made sense, that would be really helpful. If nothing makes sense, I'll actually take this into this video and re-record it because I'm still learning this myself. And then we're going to say, if we are not alive, we're going to set ourselves, we're going to say dead is equal to true. The reason I split up the variables is because it helps when we go to our main scene, and it makes a lot more sense in our main scene to use the variable dead than alive. And that's the only reason I did it like that. But other than that, we're going to keep on going, and we're going to say, now we're going to figure out our die function, because if we are not alive, we're obviously dead. And the way we're going to make sure we are dead is we're going to say, we're going to say our dead is equal to true. So we are not dead. If dead is equal to true, we are dead. So this will not run. And then we're going to calculate our fitness. And the fitness function is basically determining how far away are we from the goal. If we're over here, how far away are we from the goal? That's all our fitness function is determining. That's how we determine the fitness or the viability or how likely that creature's genome is going to be considered global.best DNA. That's all we're doing. And the way we're saying that is global position.distance squared to goal.global position. And don't take my word for it, but take the Godot doc. They say this method runs faster than distance 2 because we are basically doing Pythagorean theorem, and instead of doing a squared plus b squared equals c squared, we're just not even going to be, we're not going to consider c as squared, we're just going to consider as c, because we're not square rooting it after we're done with it. So that's all we have to do for fitness. And after we're done with this, we just have to say, when is the creature dead? The creature is going to be considered dead when it enters a body. What does that mean? If I go over here and I connect the signal, body entered, connect, it takes me right over here, and it literally says, if this creature enters a kinematic 2D, static body 2D, rigid body 2D, if it enters that, consider it dead. So if body, then we're going to say dead equals true. And then we're also going to say, if the creature enters the goal, we're going to consider it dead. And the reason we have to consider it dead is because if it touches the goal, we have to calculate a fitness function. So we make sure we can get the idea that, let's say this is our goal over here. I'm just getting out of this mess. If a creature is like right here and it dies, that distance function is really small. It's probably like 12 pixels, but then it's actually 144 squared pixels. And that will help us make sure that this guy's genome passes on to the next generation. Or actually, I should be drawing it up there. Passes on to the next generation. So we can make sure this guy's genome passes on, and we have a perfect direction list or direction array to get to our goal. Surprisingly enough, this is all we really need to do to make a good creature. Like, this creature is ready to start moving around in a scene, and that's all we have to do. If anything doesn't make sense, please comment down below. I'll make sure to help. Other than that, let's move on to our main scene. So in our main scene, you can see I have my script over here, and we're going to get a declaration to a couple of variables. We're going to get a declaration to our C folder or creature folder. This is just the creature folder. It's just a node that will house all our creatures. We have a goal, and that's our goal variable over here. This is this is the goal. This is all it is. And then we have our spawn amount, where this is how many creatures we're going to spawn. In the ready function, all we're going to say is print the generation we are on. We are on gen global.generation number, and we're going to call the randomize function, and then we're going to call the spawn function. We haven't made the spawn function, so let's do that. So you can see we're using logic that's really similar to the creature, where we say if the global.bestDNA exists, and if it doesn't exist, do something else. So if the global.bestDNA doesn't exist, we're going to this statement, and we're just going to say for I in spawn amount, we're going to create an instantiation of a creature. We're going to say creature.original equals to true, creature.alive equals to true. So this is where we're actually setting the creature to be alive. And then we're going to say C folder.addChild creature. This is important because the way this logic is set up, the way I actually programmed it, we're actually going to be looking through our C folder, which is our creature folder, and we're just going to be looping through them and finding the best fit creature. We can't really do it. There are ways to do it if we just add it to the parent. If we just do .addChild creature. In fact, if we just do add child creature, we'll add it to the main scene, and then that makes it slightly harder to loop through the creatures. So we're just going to add it to a folder. And this is for creatures who are original. These are the original people, or first generation. If you are not first generation, then global.bestDNA must be true. If it's true, then we're going to be going through the same idea. We're just going to make for I and spawn amount. We're just going to make a creature. We're going to set original equals to false. We're going to add it, and then we're going to say for each creature and get child for each creature in the C folder. After we've added every single creature to that folder, we're going to say creature.alive equals to true, then creature.dead equals to false. The reason we have to say this is because if we do not, for some reason on my computer, if I let this program run without these 3 lines, if I let it run like this, what happens is, if I let it run without those couple lines of code, what happens is, as soon as a creature spawns in, it starts moving. As soon as the next creature spawns in, it starts moving. So you can see that the first creature will be probably next to the goal, while another creature is spawning. Another creature just might have spawned, and this first creature, so this is the first one, and this might be like the 75th one, is just starting to move, and then this first creature just already got to the goal. That doesn't make it fair because this 75th one never got to express its gene because it obviously was killed within a matter of seconds after being spawned because the first one already touched the goal, or maybe everyone else has finished moving, something like that. But we have to make sure everyone gets to express their gene because maybe 75 has a direct line to the goal. We'll never know. So we have to make sure we allow every creature to start after every other creature has spawned in. I'm hoping I'm still making sense. And then the final function is going to be on the timer timeout. So I know this looks kind of convoluted, so I'm actually going to collapse a couple functions just to make it a little bit easier to understand. So this is the final function, and you can see in our timer variable we have our auto start on, and we have our signal connected, and we're going to be saying dead amount. I should actually replace that to dead amount, but this is for the number of creatures who are dead. We're going to be saying for creature in C folder.getChildren, check if the creature is dead, and then add 1 to the dead amount. This is actually dead amount. I should really replace that, but so that's all we have to do. So then remember, this is happening every 1 second. Every second we're going to be checking how many creatures are dead. If the dead amount is equal to spawn amount, which makes sense. So if everyone's dead, then this statement must be true. If everyone is dead, so then we're going to check for a closest person to goal, and I don't know why AVE is there, but and their fitness. That's all we're going to be checking if this condition is true, which means everyone is dead. So then we're going to say var best fitness so far is a really big number because the bigger the number, because remember the fitness function, basically our fitness function in this specific example basically says if the fitness is really big, you're not really fit. If the fitness is really small, like 144 or maybe 250, you're really good, right? That's all we're saying. So we're going to start off with a big number, and then we're going to say var ID of the minimum. This is the ID of the creature folder. So in the creature folder, we're going to add our creature. So we're going to say, we're just basically doing that. So this will be the first creature. This will be the 0th creature. We're just going to be getting the ID of which creature we're looking at. Then we're going to say we're again looping over the creature folder, and we're saying we're going to, instead of doing get child, we're doing get child count, so we can get I as a number. We're going to say var fitness is a type of float, and we're going to say C folder.getChildI .fitness. We're getting the fitness of each creature in our C folder, and then we're saying if the fitness is less than the best fitness so far, set ID of min equal to I and get best fitness so far equal to fitness. The reason we're doing this is because we have to make sure we get the best fitness out of all of the creatures. So now we found, after this loop is done, we have found the best fitness. So get the best fitness and save it. So get the best fitness and save it. So then we're going to say if global.bestFit is greater than the best fitness so far, because remember, we don't want to work with someone who is less fit than the previous generation, because that doesn't make sense. Then we're going back in evolution. We want to go forward in evolution. We want to get better. So we're just doing a quick check to see if global.bestFitness is greater than best fitness so far, and then we're going to say global.bestFit equals best fitness so far. This is the best way to get our fitness value to be smaller, because we're just saying if the global.bestFit is bigger than the best fitness so far, then we're going to set it equal to something. If it was smaller, so let's say it was like this, then we're saying if the global.bestFitness is smaller than the best fitness so far, then we'd be finding the worst creature. This is really important. Then over here is global.bestDNA, and we're basically going to be saying cfolder.getChild, ID of min, so we're going to be able to get the specific creature over here, and we're just going to say .genome, because in our creature, remember we have this genome, that's all we're getting, and we're going to be saving it in our global script, which does not get reset after a getTree.reload getScene. And then we're going to be saying global.generation number plus equals 1. Now if we run our scene, we should not have any errors, and of course, I can't believe I spelled something wrong in the two scripts. And now you can see that we're actually printing out a bunch of stuff that we should not be, and that's actually lagging the computer a little bit. If you want to find everything in the file, there's a quick tip. Do Control-Shift-F and do print. It'll actually find all the instances of print. So that's commented out, that's commented out, that's not commented out because we actually want to see which generation we're on. And once we run the scene, we can see that we have our creatures, they're all moving around like crazy, and eventually the scene stops. And you can see right here, this is the exact reason the program is lagging, because we actually put creatures in our C folder, which we should not have. And now when I run the scene, so now everything should work when I get these 3 lines back in, because remember I said it would not work if I did not keep these 3 lines in. So now everything should work. And now you can see everything's working. And of course it's lagging just a tiny bit because I'm recording. I have some other recordings that I'll show after, or maybe I'll post as a separate video. But you can see our creatures are learning from their past experiences, and now they're able to get to the goal. Now you can make your tile map. You can set up your tile map to have extra features like this. So now the general path will be like this, and the creatures will actually respond to that. And in AI, as far as I can tell, when you have something like this, where this is a potential solution, because think about it, these creatures have no sense of their surrounding world. And you can see they're actually getting stuck here. This is called a local minimum. This is a local minimum, and the creatures are getting stuck here. But now they're able to, through pure chance, they were able to figure out, hey, maybe this is actually the closest point. So then this is another local minima, because they can get stuck here. And they're actually figuring out, hey, maybe that's not the closest point. But they're still trying out, and they're still mutating, and they're still working it out, and they're figuring it out. And they're saying, no, this is still the closest point, but we're not getting any closer. So no mutation has been, there have not been any good mutations left. And you can see it's still moving around. It's not figuring out any good mutations. So, and now it's found a good mutation. Now, multiple of them had a good mutation. Now we'll see more of them actually sticking onto this goal position. The reason people still get stuck here is just by random chance, a lot of them get stuck. And we can see they're still getting stuck, but you can see a lot of them actually went over, and that's actually a lot of people who went on to that goal. But on that previous generation, not a lot of people went on. So of course there's imperfections. You can say after we've reached the goal, make sure the generation or the mutation rate is really small. One way you could do that is by saying, we can do something like if the global.best fit is less than maybe let's say 1,000 or maybe 500. We can say something like the mutation amount is equal to 0.01, and I'll run this and I'll show you guys the results. So now you can see that we've actually been able to hit the goal, and I'm not exactly sure, I should have printed out the fitness, my mistake, but you can see that we're getting a lot closer to the goal. And I think an issue popped up where we lowered the mutation rate enough where the creatures no longer understand, or maybe we didn't. But remember, this is all AI, and really no one we understand what's going on. But when I say we, I mean the experts in the field. They even admit that they have no idea what's going on inside the neural network or a certain algorithm, just because of the nature of math and how many numbers there are. But over here we have a sense that these creatures are slowly figuring out how to get to the goal, and just because they're always being mutated, as you can see. We're going over here and we're saying else if you're a second gen or third gen or something gen, then you're going to be mutated each time. That's just how we've set it up. That's how we set it up in this example. But if you would want, and I highly recommend, maybe set up an algorithm to determine the mutation amount. So how far you are, if the creatures are over here, set up a different mutation amount. Whereas if the creatures are over here, set up a different mutation amount. And this is just my example. If you have any questions, please comment them down below. I'd love to answer a question because I want to help people understand really complex concepts. That would be a really cool thing. On top of that, this code will be on GitHub, so please copy it, play around with it. It'll be in its own repo, so please make a fork of it, start, whatever, because I really want people to understand, like, hey, this genetic algorithm is possible to make on your own computer because I don't have the best computer in the world. Like you can see when I run it, Godot will literally tell you that I have a GT 1030. So you don't need a Titan RTX 3090 4000 Super to run this program. You just need a computer and you can start making cool things. That's all I really want to show, and that's all I really want to share. And have an amazing day. Original person. Hello everyone, NadLabs here. Today we're going to be making this AI in the Godot game engine. As you can see, this program is able to learn from its past behavior and is able to correctly identify the goal, move toward it, and get better. Shit.